Alright guys, this is application of the equilibrium constant. So we're going to talk about the equilibrium constant and what it means, and then we're also going to look and see if certain reactions are at equilibrium. Okay, so why is the equilibrium constant important? It's important because it tells us how far to completion the reaction goes, right? So we can kind of predict how much product is going to be produced based on our equilibrium constant and the value of it. All right, and so in more specific terms, it says, what does it mean if you have a large K? Well, let's say I have this equilibrium between A and B, and my K is like 1 times 10 to the 9th, which is 1,000,000. So it's huge, right? And this is the concentration of B over the concentration of A. Well, that means that I've got tons of B, tons and tons and tons of B, and very, 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 very little A. And so that would mean that this reaction is product favored, okay, which means it makes lots of product. So no matter what you put into the reaction vessel at the beginning, if you put product in it or if you put reactant in it, if you put reactant in it, most of that reactant is going to convert over to product. If you put product in it, most of it's not going to react because it's very much product favored. So it produces lots of product. Okay, and then if we look at what does it mean if you have a small k? Well, the same is true if we have a different reaction. Okay, and if our k is 1 times 10 to the negative 20, which means it's 0.0000019 zeros, 1, which means that if D over C, okay, then that means that the D product is very small. There's hardly any D, and there's tons and tons and tons and tons of C. And so that's making this really, really tiny, all right? And so we call that reaction reactant favored. All right, and that just means that it produces lots of reactant. Okay, so just like in the one above it, if we were to put reactant in the container, it would stay mostly reactant and produce very little product. And if we were to put product in the container, most of the product would end up turning into reactant because the K is so tiny. Then that means we have to have lots and lots of reactant. Okay, so if we have a mixture with the following concentration, so it says here that our Kc is 57, and we have H2 is 0.1, I2 is 0.2, and HI is 0.4. Is this at equilibrium? Well, I don't know, but could we find out if it's at equilibrium? Sure, we could find out. We would just have to see if this, plugged into the equilibrium expression, gives us K, right? So it would be 0.4 squared, because the equilibrium expression is Hi squared divided by hydrogen divided by iodine, and that gives us K if these are at equilibrium, right? The concentrations have to be at equilibrium to give us K. So we don't know if they're at equilibrium or not, so we're just going to plug it in and see. So that gives me 8, right? If I take 0.4 squared and divide by 0.2 times 0.1, that gives me 8. Well, that's definitely not Kc, so it's not at equilibrium. All right, and so let's look at that a little bit closer. What we just calculated was something called the reaction quotient. And the reaction quotient is use the letter Q. Now, we find the reaction quotient in the same way we find K, but it's not necessarily at equilibrium. We don't know if it's at equilibrium, so we can't say it's equal to K. So we're just guessing, and so we call it Q, the reaction quotient. All right, and this will come back up later. And students always forget what it is, so try to retain what that is. Okay, so these concentrations are at any time during the reaction, or if you're unsure if it's at equilibrium or not. Okay, so this is the same problem that we had on the previous slide for this reaction with a Kc of 57, and then we had these concentrations. So we plugged them into a pretend K, which happened to be Q, and we found that it gives you a Q value of 8. And so since it's not equal to K, so since Q is not equal to K, it's not at equilibrium. So which direction, so if it's not at equilibrium, that means that this reaction is still active. It's still moving in one direction or another. So now we need to kind of figure out which direction it's going to go. So since my Q, right, is 8 and my K is 57, that means that my Q will continue to get bigger until it reaches K. So Q needs to get bigger until K is reached. And the only way it's going to do that is if the reaction here starts to move in the forward direction and makes more product, so that this top gets bigger, and if it's making more product, then this reactant stuff is getting smaller, and so this would get smaller. And then that would make this number get larger because we have a bigger top than we have bottom. Okay, so this is a summary of that, right? So how will the reaction proceed? Another way to say that is which direction will the reaction go? If the reaction is not at equilibrium, you have to ask yourself, does Q need to get bigger or does it need to get smaller? And so that will tell you which direction you have to go to achieve equilibrium. If Q is smaller than K, the reaction is going to go forward. And if Q is greater than K, it has to get smaller, right? So it's going to go in reverse. It's going to make more reactant and eat up product so that the top, right, because it's product over reactant, is your Q. If the top gets smaller and the reactant gets bigger, then the Q will get smaller until it reaches K. All right, so for the first example, I have water and dichlorine monoxide reacting to form hypochlorous acid. So which of the following sets of conditions is the system at equilibrium? For those that are not at equilibrium, in which direction will the reaction shift? So in number 1, right, my K is equal to hypochlorous acid, divided by the concentration of Cl2O and H2O, right? And we find that it is 0.0900. And this is at 25 degrees Celsius. And so here, this is happening at 25 degrees Celsius, and this one is happening at 25 degrees Celsius. So the temperature is not changing, because if the temperature changes, we have other issues. All right. So I want to know if this is at equilibrium. So in order to find out, I'm going to calculate Q. And so Q for this is going to be equal to, since it's 1 liter, then this means these are all molarities because we would divide them all by 1. So that would be 1 molar divided by 0.1 molar times 0.1 molar, right? Because this is Cl2O, and this one is H2O, and this one up here is HOCl. And so this one is going to be squared. So I have 1 squared divided by 0.1 times 0.1. So that's going to be 1 divided by 0.01, and that is 100. So since Q is greater than K, the reaction has to go to the left. So reaction shifts left or proceeds left until equilibrium is established or is met, right? Okay, and so the way that I know that, one, you can either memorize it. All right, so I always write Q before K, and if the greater less than sign is opening up towards Q, then the arrow has to go the same direction. So if I think this of as an arrow, then this is going the opposite way of this guy. All right, but I hope that you would try to understand what was happening. So since this number is so big compared to this number, we need it to get smaller. And the only way to get it smaller is to make the top smaller and to make the bottom bigger. So if I want products to go down and reactants to go up, then I have to make more reactants. So I have to go towards the reactants. So that's number 1. And then number 2 says we've got a 2-liter flask and we have 0.084 moles of HOCl. So I'm going to have 0.084 divided by 2 liters. And then 0.080 moles divided by 2 liters, and that's of Cl2O, and then 0.98 moles divided by 2 liters, and that's going to be the concentration of water. All right, so this is going to give me 0.042, and this is going to give me 0.040, and this is going to give me 0.49. So if I plug those in for Q, it's going to be 0.042 squared divided by 0.040 times 0.49. So I get 0.09 is Q. And so since this is exactly this, that means that this reaction is at equilibrium. So it's at equilibrium, so it's not going to react anymore, right? It's flatlined. It's done reacting. All right, so this is the last one, and I know that this looks like a lot, but it's really not. So stay with me because this one is different and weird. All right, so we have a Kp equal to 1.04. Here's our reaction, and I'm going to write my Kp expression really quick so that I'm not taken off guard later. And so my Kp expression is going to be the pressure of carbon dioxide, and that's it, right? Because this is solid, so it's not in the Kp, and this is solid, so it's not in the Kp. And it says calcium, so at low temperature dry ice, calcium oxide and calcium carbonate are introduced into a 50-liter container. So we put all of this into a container. The temperature is increased to 900 degrees Celsius. That's this temperature for which that K is correct. And it says resulting in the dry ice converting to gaseous carbon dioxide. For the following mixtures, will the initial amount of calcium oxide increase, decrease, or remain the same as the system moves toward equilibrium? So I'm going to rewrite this reaction over here so that I can draw next to it and make it easier for y'all to understand. So for number 1, I'm going to find Q. So my Q is simply going to be 2.55 atm. They give you all of this to throw you off. Okay, it doesn't matter that you put that in the container. Now the calcium carbonate has to be in the container, and the calcium oxide has to be in the container if the reaction is going to shift one way or the other, but it doesn't affect equilibrium. So if my Q is equal to 2.55 and my K is equal to 1.04, then my Q is greater than K, and so the reaction is going to shift to the left. And so if the reaction is shifting to the left, then that means, because it doesn't say which direction does it shift, it says, well, the initial amount of calcium oxide increase. So calcium oxide, this one, is this, right? And if the reaction is going this way, and we have 95 grams of calcium oxide in here, right? Then if it's going this direction, this amount is going to go down. So this is going to go down for number 1, because the reaction has to shift away from it. It has to make this, and the only way to make that is to use up some of this. All right, so let's look at number 2. So my Q is going to simply be 1.04, right? Because it doesn't matter, because these are solids. They're not in the equilibrium expression, right? Because here's the equilibrium expression. K is equal to pressure of carbon dioxide. The reaction quotient expression is going to be the same thing. Q is equal to the pressure of carbon dioxide. It's the same thing. It's just not necessarily at equilibrium. And then when we look at this, if Kp is equal to 1.04, well, Q is equal to Kp, and so this is already at equilibrium. It's not going to shift at all. All right. And then number 3, we have the partial pressure is equal to 1.04. So even though we've got 5,000 grams of calcium oxide and only 0.14 grams of calcium carbonate, this one is going to be at equilibrium as well, right? Because my Q is equal to K. And so it's not going to shift anywhere. It's not going to go any direction. It's happy where it is. And then the very last one here, number 4, my Q is going to be equal to 0.211. And so if Q is 0.211, that means that Q here is less than K. And so if it's less than K, my Q needs to get bigger until it becomes equal to K. And so the only way to make Q bigger is to make the products more. And so this time the reaction that's written up here is going to shift to the right, right? So on number 4, the reaction is going to shift this way. So it's going to consume calcium carbonate. So even though we have 715 grams, in this one. All right, even though we have 715 grams of calcium carbonate here, we want to make more product because the reaction is going to shift towards the product. So that means that calcium oxide, that's what it's asking about, is calcium oxide, is going to increase. So to go back and summarize, on this first one right here, calcium oxide will decrease. Here, calcium oxide will remain the same because it's at equilibrium, so it's not going to change. Here, it's at equilibrium, so it's going to remain the same. And then for this one, calcium oxide amount is going to increase because it's going to go toward the product and make more product. All right, that's it.